Assalamu alaikum, dear students. Welcome back to multivariable calculus series. We are already done with chapter 11. Now we are ready to study something even more interesting, and that is study of objects that move through space. Imagine an airplane flying through the sky, a satellite orbiting Earth, a drone delivering a package, or a particle moving in physics. How can we describe their motion mathematically? A simple function like y is equal to fx is no longer enough because the object is moving in three dimensions simultaneously. Instead, we use vector valued functions. And this is chapter 12 of the textbook. A vector valued function tells us where an object is, how fast it is moving, in which direction it is moving, and how its motion changes over time. Throughout this chapter, we'll be studying vector valued functions, their calculus, arc length, unit tangent, normal and binormal vectors, curvature, velocity, acceleration, and much more. By the end of this chapter, you will have the mathematical tools used in robotics, computer graphics, aerospace engineering, and mechanics. So let's begin with section 12.1. Before getting into mathematical formulas, suppose I ask where this car will be after 5 seconds. Giving only the x coordinate is not enough. We also need the y coordinate. And if it is flying, we need the z coordinate too. So instead of one function, we need three functions working together. So this idea leads to vector valued functions. By the end of this lecture, you'll be able to define a vector valued function, evaluate vector valued functions, sketch the curves of such functions, understand the domain and range of these functions, interpret vector functions as motion. So in general, a function is a rule that assigns to each element in the domain and element in the range. But a vector valued function is simply a function whose domain is a set of real numbers and whose range is a set of vectors. So we are interested in vector functions R whose values are three-dimensional vectors. This means that for every number t in the domain of R, there is a unique vector in 3 space denoted by RT. So in 3 dimension, we know that vectors can be represented by their components x, y, z, where x gives horizontal position, y gives sideways a position, and z gives height. So instead of constants, each coordinate can depend on time. So that gives us the vector valued function with components depending upon t. So Rt is vector valued function whose components are ft, gt, and ht. So this is called vector valued function, where ft, gt, ht are ordinary real valued functions. And each coordinate changes with t. So unlike ordinary functions, the output is not a number. The output is a vector. So if we have input a number, then we get an output as vector. Okay, let's discuss these functions with the help of few examples. So first of all, we have an example of vector valued function. Rt is equal to t cube. natural log of 3 minus t, and square root t. And we are required to find the domain of this function. So domain of this function would be the domain of combined domain or common domain of all these functions. That is, all the values of t for which ft, gt, and ht all are defined, right? So here ft is equal to t cube, gt is equal to natural log of 3 minus t, and ht is square root of t. Now ft is defined everywhere, that is t cube is defined everywhere, but gt is defined when 3 minus t is greater than 0, and this means t is less than 3. And ht is defined when t is greater or equal to 0. So this gives us an interval 0, 3. So 0 is included, closed from 0 and open from 3. So this is the domain of this vector valued function. Similarly, we have another vector valued function, rt is equal to cos ti plus sin tj plus tk, and we are required to draw the curve of this function. So in this case, x is equal to cos t, y is equal to sin t, and z is equal to t. So if we square x and y and add both the square terms, then we get 1. That is, x square plus y square is equal to 1. So our curve must lie on the circular cylinder. So if this is a circular cylinder with radius 1, then the points on the curve would lie on the circle, right? So let's try how can we find these points. So for different values of t, we have different points on the curve. So on xz plane, xy plane, sorry. On xy plane, we have z is equal to 0, that is t is equal to 0. So when t is equal to 0, cos t is 1 and sine t is 0. So that point would be 1, 0, 0. So we'll start with 1, 0, 0 on xy plane, and then we'll move around the cylinder by having different points. So if t is equal to, for example, pi by 4, then we have sine pi by 4, which is square root 2 over 2. Similarly, cosine pi by 4 is also square root 2 over 2. So, and if we have t is equal to pi by 2, then we'll draw this point on xy plane. X is equal to cosine pi by 4, y is equal to sine pi by 4, and we'll give height to this point uh, along the cylinder. So that height in this case would be pi by 4. Similarly, if we have t is equal to pi by 2, then x will be cosine pi by 2, y will be sine pi by 2, and its height, this point, height of this point would be pi by 2. So this is how the curve will look like. For different values of t, we have different points around the cylinder. So as t increases, the spiral goes upward around the cylinder, and this curve is called helix. This curve is called helix. This is the helix. Okay, let's have another example. We have another vector function, rt is equal to t squared t cube, and its curve is called twisted cubic. We'll see how would it be drawn. This is also a curve of intersection of two surfaces. Y is equal to x square, z is equal to x cube. So if we draw these surfaces, the curve of intersection would be this curve. So here x is t, y is t square, and z is t cube. And if we draw this, we have this curve. Okay, let me show you the GeoGebra drawing of this curve. So first of all, let's draw y is equal to x square. This is the surface y is equal to x square. And then we'll draw the surface z is equal to x cube. This is the surface, and the intersection curve is the t square t cube. So this is the curve. Twisted cubic. So you can also draw and see this curve in GeoGebra. Vector equation of a line segment. We are already familiar with the vector equation of a line. That was R is equal to R naught plus TV, where R naught is the position vector fixed point on the line and V is the vector parallel to the line. But if we have another point R1 on the line, then its position vector P1 on the line, then its position vector is R1, then this vector would be R1 minus R0, and that will give us the direction vector, and the equation becomes this: R is equal to R0 plus T times R1 minus R0. So instead of V, we use R1 minus R0 for direction of the line. So we can simplify this by this expression: 1 minus T times R0 plus T times R1. So for values of T between 0 and 1, this actually gives us the points within points on the line within these 2 points, these 2 endpoints. So this is the vector equation of line segment joining 2 points. So T should lie between 0 and 1. So within this interval, we'll get the points between these 2 points on the line. So whenever we are required to find the equation of line segment between the points, between 2 fixed points, then you can use this equation. That is, R is equal to initial point R0 times 1 minus T plus T times terminal point R1. So when T is equal to 0, you will get initial point, and when T is equal to 1, you will get terminal point. And for fraction values of T, you will get any point between these 2 points on the line. So that's all for today. See you next lecture. Till then, take care. Bye.